Hi everyone, today we will be studying a sampling method called the inverse probability transform. So the setup of this problem is as follows. We want to sample from a probability distribution. So recall that in the case of distributions, the PDF, which is the probability density function, gives us the probability of P of x equals x, right? So P of x equals x. This is the PDF of our distribution, right? So maybe it looks like this. There's also an associated CDF, which is the cumulative density, which gives us another quantity which looks a bit like this, right? So this is the CDF, and it looks a bit like this. It's always increasing in value, and the maximum value it can achieve is 1.0, and the lowest value is 0.0, right? Now, finally, the inverse CDF is just the inverse of the CDF. So if the CDF, this function, is f of x, then what we want to know about what we're given is the inverse CDF. Inverse CDF would be f inverse of x, right? So in this problem, we are given the inverse CDF of the distribution, and we want to sample from this distribution. So the process is actually pretty simple. What we do is we choose a uniform random number. So let's say we choose a uniform random number u, which is sampled from the uniform distribution from between 0 and 1, and whatever we choose, this will be our y value. So what we do is we pass this as an input to the inverse CDF function and get the x value, right, which will be the sample from the distribution as we want it. So what I mean is, let's say we want to sample a number between 0 and 1, let's say it's 0.3, right? So 0.3, when you sample and you kind of see the inverse CDF function, you pass it, because it takes as argument something between 0 and 1, you give it a value of 0.3, and it will spit out a certain number, which will be the corresponding sample that you wanted, right? So all you have to do is kind of just take a bunch of uniform values like 0.6, and the kind of samples you're getting are just sampled from the using the CDF function, and so it's a very simple process, right? And we can show that the samples that we arrive at using this process correspond to the samples from the original distribution that we wanted. So this distribution, right? Okay, so let's try to prove this. And how do we prove this? Well, we need a simple fact for this, and that fact is that the CDF of a uniform distribution, so uniform random variable at a point u, is just the probability that u is less than or equal to u, is actually just, if you integrate, and the density is just 1, right? Because the uniform distribution kind of just looks like a straight line, right, at 1, and this becomes equal to u, right? So we know that the CDF of u, when you evaluate at a point, it's the value that you're evaluating it at. So we can use this fact to kind of show why the samples that we are obtaining are actually the right samples, right? So how do we show that? We just say the CDF of the random variable that we are trying to get samples of at the point that we're trying to get samples at is equal to probability that the random variable is less than or equal to the value. And now what we do is we kind of notice that how we're generating the samples is that we're taking the u's and putting it on the y-axis here, right? And then getting an x value, right? So we're passing it basically through f inverse function, and we're getting an x, right? So in terms of the random variable, what this means is that random variable x is f inverse of u, right? And if we just put this back here, we will get f inverse u is less than or equal to x. And taking the function to the other side, we have u is less than or equal to f of x. And using our result that we just showed, we know this is equal to f of x. So the samples that we're getting, the CDF of that is exactly equal to the CDF of the distribution that we wanted to compute the samples for, right? So this is exactly the inverse of the inverse CDF that we were given, right? And that sort of proves this technique. So yeah, thank you so much.